Hello everyone and welcome to Handmade Hero, show where we code a complete game live on stream. Before we start programming today, I just wanted to update some software on this machine. Two Handmade programs that we use actually, Milton, our drawing program, and Remedy, our debugger, both made in response to the series actually by programmers who did some really great work. We use both of these on stream regularly. So I'm going to go ahead and update our existing copies with these copies. The update to Remedy is not something we actually need at the moment. It's something that is, I think it has like some new features and some fixes. I don't remember exactly what was in 2.8.2. I think it fixed some string printing stuff. There was some stuff that I actually very specifically needed at work, I remember. But I just don't remember exactly what they were. But we were not having any issues on the stream with it. So this is not an update to address anything that we were doing. It's just might as well get up to date so that we don't run into any problems. Milton, on the other hand, is actually an update that was made in response to something I requested. I said it would be great if I could stop drawing lines on the screen myself for grids and just have a thing that drops down a grid. And that was actually made. I don't actually know the person's name who made it. I only know their Twitter handle. Excuse me. But thanks here goes out to Amin Sayeg. I guess, I assume that's their actual name. I don't really know. But at AMEENSAYEGH, if you go check that out on Twitter, that's the person who actually wrote in and patched Milton for us. They made their own version that has the tool I asked for on stream, which is a way to lay down like a regular grid, because I do that a lot, and of course drawing lines accurately is not my forte, and you want like a bunch of equally spaced ones for doing things like here's a pixel array or whatever. So that's pretty awesome, and we're going to try it out. We'll just see how it works. But basically, in the Milton directory, I guess that was in the root here. I should probably move the Milton directory into the apps directory, actually. Should start getting into that habit. There we go. So this was the old Milton, and, there is no such tool. This is the new patched version of Milton. We'll give it a shot. Here it is. I guess this thing here is sort of a brush window that gives us the option of drawing a grid. You can see the G key here. So I guess if I do G, I'm on grid. So it looks like it's pretty easy to stamp down one of these. Looks like here's what we were working on. So it looks like if I just set the brush size low, and then I set maybe a standard size here, I don't know, something like that, then it would be pretty easy for us to slap down little pixel grids. And so that just, I think, makes things a lot easier. And it would make my diagrams a little more clear because, they're usually pretty messy. And so if we just have a way to do that. So if I'm drawing, let me just test it here. If I'm drawing here and then I just hit G and then B, that seems nice, right? Because then I can just slap one down. So thank you very much, Amin, for that. And I think that's probably all we need. If that makes sense. I guess one nice feature that maybe we should go in and add, since everyone else did all the work here, if we switch to grid, the opacity I assume is the same as it was on the brush. So if you go to 50%, and then you switch, oh no, it's not. Wow, That's great. What I was going to say is we could leave the opacity of the grid sort of locked down at something less, so that when we stamp it down and then we switch back to brush, it's like a dim grid. Because usually we don't want the grid to be too bright, probably. That's great. So let's say we set it down to something like that. And then I just go like this. And then we've got a nice little dim pixel grid. Then we come up here. That's great. I don't know what lines does. All right, so it looks like we should probably be taking advantage of this as well. I don't know if this was added or if this has always been in Milton, but I should probably get used to doing L as well. Just looking at that. Yeah. All right, so we've got some nice new tools. B, G, and L. I'll remember those. That's B. That's G. That's L. Let me try it with the actual pad, just to make sure that nothing has broken there. It looks a little different, like there's it's definitely, no, I guess it's okay. No, it definitely looks a little weird. I wonder if this is just a version of Milton issue 162G1. It's definitely like not doing, it's not as smooth as the other one was. Yeah, it's not like, and there's a lot of little like laggy there. Something's wrong with this. Do you guys know what's up with that? So I would be interested to know what's going on there, because the previous version was fine. This one looks kind of a little bit busted. We could update the pen drivers as well. I don't want to do that on stream. But maybe let's try to do that. Here's what we'll do, because I'd like to start programming. It's been too long trying to update this. So we'll take a look and see. I'll just leave that up, and then hopefully we'll see that when we go to shut down or something, and I'll update them after the stream's over. Seems like a fair idea. Okay. Let's do this. So where we left off, we kind of made a pretty cool utility, this is where we stopped last time we were programming. We made a cool utility that generates sampling spheres. And I want to say it was looking pretty sweet, actually, when we stopped last time. And basically, it just writes them into our executable. So it writes them into our it puts them as like an array directly into our code. So it compiles into our executable, and you can see it's a very nice like sampling sphere. The colors on the sampling sphere are the different frames on which the samples will be taken. And you can see the sphere is really nicely covered there, I think. And the colors are pretty well distributed, right? You don't see any patterns really to the colors either. They're very nice and well distributed. So I think we've done a good job doing what we wanted to do, which is to make sure that we had a nice set of samples to use. And that's exactly what we've got here. So I think we are now ready to proceed to the final stage of the lighting process before optimization, which is getting all of the pipeline stuff working properly so that we're actually sampling the lighting instead of previously we were sampling them on all surfaces, we just sampled them at probe locations now. And the biggest problem that I have with the way that we're doing things now, we're also going to try and think of if there's anything we can do to address sort of the one thing that feels still a little bit squinky to me, which is that if you look at how we're doing the lighting at the moment, and you go in here to look at how... Ooh, accidentally pulled one of my keycaps off. If you look in here at how we're doing the lighting currently, one of the things that you'll notice is that the lighting itself is very efficient to compute now, I think, the way that we're doing it, because we will know directly which light, sort of where the light that we hit is supposed to be written back. Because when we look at our sampling sphere, we'll know it was going in this direction, so it should be added to this set of this should be added to this set of light probe information. But what's kind of nasty is when you have the light probe set up the way we do, where you've got 6 directions of a cube, it's really not particularly good, because 6 directions of a cube is exactly a multiple of nothing SIMD-wise, right? It just doesn't make for a particularly clean way of doing things. And obviously we have another problem, which is that SIMD can't do memory accesses, so we have to downshift there, but that's unavoidable. So no matter what we do, that's going to happen. So it's really just the fact that I don't love how weird the the fact that our lighting samples are 6 directions. They're the faces of the cube. So here's a thought. I just randomly had this thought sitting here, and it may be a terrible idea. I don't know. But what if we instead just say there were 8 directions, so that instead of being 6, it's 8? I know this sounds a little weird, but I just thought of it randomly in my head. So, I should also make sure this is pinned to the taskbar. Oops. Or it probably was already pinned to the taskbar. So here's this sort of weirdness. So 8 wide light probes. This may already be a thing in the literature. I don't know. I haven't read up on it because I intentionally didn't want to, so we could try a crack at it ourselves on the show. But here's one thing I'm thinking. I intuitively, just when we were typing in the code, I was like, well, if I'm going to probe light, let's pretend I have a cube, and we'll have each face of the cube, you know what I'm saying? We'll record the light that's incoming on each of the faces of the cube. Well, a cube has 6 faces, so if you do that, you are talking about 6 wide light sampling. And so no matter what your situation is, if the lights have colors or not, you're talking about taking 6 and multiplying it by something. And the only something that you could multiply it by in order to make it be aligned to 4 wide SIMD lanes, right? Wow, that's really going to bug me, those little loops there. Hopefully we can fix that. Those 4 wide SIMD lanes, the only way, there's no real way to ensure that other than multiplying this by 2, right? Because if we wanted to make sure this number was divisible by 4, well, 6 is 2 times 3, 4 is 2 times 2. They have one common factor, which is 2, but this 3 here means that we would have to multiply this by 3 in order to make a common multiple, right? So basically what would happen here is we'd have to have 12 light samples in order to make sure it was divided by, multiplied by 4. And I'm not even really sure what those 12 would be. It would be 2 samples per face or something, right? But you can see why it doesn't really line up with SIMD lanes particularly well. If I wanted it to, it doesn't really. And so I don't know that it necessarily matters much, but I kind of think we do want it to line up with SIMD lanes. And the reason is because if you think about how these light probes work, I don't really know that you can quite do them in parallel very well, because you're going to have to downshift to do your memory lookup. And when you do your memory lookup, you're doing a different cube for every ray that got intersected. And maybe the answer is, well, then you just load from all 4 of those and do the adds 4 wide at a time. And, you know, thinking about that in my head, that it seems plausible, I guess. But it would probably be nicer if we didn't have to do that, because it makes the code a little bit uglier if all the operations have to be strided across 4 light probes all the time. So what I was thinking is, well, another option is to observe the fact that although a cube does have 6 faces, it also has 8 vertices. And 8 vertices, that is actually aligned to 4 wide SIMD lanes. It's 2 SIMD lanes exactly, or 1 AVX lane, right? So maybe that's a little more interesting. And if you think about how that would be arranged, we actually could more or less keep a pretty simple, a pretty similar lighting scheme to what we have if you imagined lining up the cube a little differently. So we just said, okay, here's how this is going to go. You know, we have some kind of a diamond shape, right? And then along the other axis, we have another diamond shape, right? So here's 2 tetrahedrons that form the faces of a cube, right? The ones that we have here. So if we wanted to have the lighting still make some sense in this organization, I'm just trying to think if there's any way to do it. You know, I was going to say we could just tilt the cube and just kind of accept a little bit of off-axisness. So suppose we have the cube so that one vertex is pointing up and one vertex is pointing down still, then in that world, so if you assume that that was this transversal here, right? Then you just get a hexagon around the other side there. So, boy, this is hard to imagine in 3D without an actual tool. Can we rotate a 3D cube? Haha, yeah. So just looking at a 3D cube here, right, if you imagine the poles being like that, then what you can see is the lighting would kind of oscillate around, like it would be up, down, up, down, up, down, like that. And I mean, I guess there's no real reason why we would even have to do that. In theory, we could make it a non-cube, so we could just make it be like 2 kind of cones, right? And I don't know that there'd be really any penalty for that. So another option, I guess, would be to do it like this instead of a cube. Where we basically said, like, okay, here's... well, we'll do it on the x-axis. Here's some fixed points, right? And as we go around here, we know that we actually want to have 6 points instead of 4. So normally we'd have those 4 axes. Instead, what we're going to do is divide it into 6. And so we would figure, you know, 60 degrees or so for each, you know? So something like this. Probably. So it would be more like there. So like thing. Something like this. Right? So we just have like a hexagon and then an up and down. And, you know, I don't know that there's any real reason not to do it that way. The only reason that that maybe doesn't make a whole lot of sense is it adds operations in the pixel shader, right? Because you figure you got to actually sample the lighting from these things somehow, right? So you have to have some way of actually asking what is the lighting at a particular point. And so, you know, you would prefer to have a way of sampling it that was as inexpensive as possible, and this perhaps isn't necessarily that thing, right? So I guess that's, you know, one reason not to do it. I don't know. I'm going to leave that for now because I don't have a strong opinion about it. It's just something to think about. Like, because we control this on both ends of the pipeline, we control the sampling of it at the head end, and then we control. We control the. They're both sampling. We control the light propagation, and so how we actually build these, we control that, and then we also control how they're sampled in the pixel shader, and so there really isn't a lot of issue there to, you know, to us coming up with arbitrary shapes that whatever would be the most efficient. Probably the pixel shader is the most important one for efficiency. So just making sure that that's easy to sample. That seems like, you know, the right idea there, but, you know, we'll see. So I guess here's what I want to do now. Moving on. Just want to get that out there. So I'd like to start sort of a bi-directional process here to try and converge on finishing up our lighting. So now that we've got our sampling spheres, we've got our light probe locations, we have our ray casting, and we need to bring these all together now to make a final lighting solution that we then optimize and try to make into something we believe we could argue is shippable, right? So what we need to do, there's a lot of things we have to do. I'd like to start on both sides of the process and kind of ping pong back and forth. On the one side of the process, we have our pixel shader, and the pixel shader is sampling the actual lighting, and we need that to be efficient and to be able to do its lookups and blends and all that stuff in a way that's reasonable. So we want to work on that, and the other thing we want to work on is getting the actual lighting solution propagating light properly. And that's the other side. And that, you know, we've already done that, but we're reconfiguring it. And so we have to like debug the new parts that we put in there and make sure that they're operating properly and that we haven't broken the ray casting and all that sort of stuff. So I'd like to ping pong back and forth between these today, tomorrow, probably next weekend, until we get everything kind of working coherently. And then we can sort of start an optimization pass on it to try and get things working more cleanly. Now, there are some issues we have. If you look at an optimized build of the game, which I can now turn on. So if I just build an O2 version here, oops. There we go. So if I build an O2 version here and look at the speed of the game, when I open up the profiler, so, you know, here's the game running as it normally would. When I open up the profiler here and I look at our frame timing, so, oops, that's the memory. Here is the timing across frames, and here is the frame rate, right? At the moment, I don't see any real issues. Oops, I don't know how to. There we go. At the moment, I don't see any real issues with stutter, but I thought we were using too much memory on the GPU. I still think we are. Not in terms of our sprites or anything like that, but just because we create too many frame buffers for the depth peeling, and we just do stuff that isn't particularly conducive to fast rendering. So if we look at this, I was going to say, I think, and it does look like occasionally we miss, I think. It does look like that to me. I don't know, maybe not. It's hard to say exactly. So, yeah, I mean, I see there's definite stutter there. Like, there's just definite stutter there. And I assume, if we took a look at what was going on, I assume that the majority of the problem there is not that we're doing anything particularly difficult for the renderer on the GPU to handle. I think it's more that what we are... Molly Bean? We got an interloping puss. Puss? What are you doing, Molly? What's going on? Do you want to look out the window? Let's see if we can distract her with the window, because otherwise she's going to start typing, and that becomes an issue very quickly. Here we go. Do you want to take a look out there? Yeah. Yeah. Why don't you take a look out there? Okay. That didn't work particularly well. What do you want, Bean? One of the problems is that Molly doesn't really know how to program, so when she types on the keyboard, it doesn't really amount to much that we can use. And I don't know that she really knows very much about lighting either. What's going on, kiddo? I'm going to see if I can get her to sit in the cat tree and give us some reprieve. Just to finish the lighting code. Just to finish the lighting code, that's all. Here you go. Do you want to come up? Do you want to come up in there? There you go. All right, so let's hope that works. Look out here. Look at how much there's good stuff out there. Go find some birds. I know you like birds. All right. I don't know. This is dicey. We'll see what we can do. So I do feel like we kind of have another issue here, which is that if we want to start working on that pixel shader, I think we're just using too much GPU memory because of all the frame buffering, and we had some things that want to get fixed there. So, like I said, just really, really big spread of things to work on right now over the next few weekends to try and dial this stuff in. And I'd like to kind of start to get a better handle on them. So one thing that I would suggest maybe we do today just to get started here is maybe we say pause on the actual lighting improvement for a few minutes. Let's go take an Nsight profile of what we're looking at on the screen here. And let's see if we can't optimize our actual rendering to the point where we know that we're not overstressing the GPU. Because what I'm worried about is when we go to put in the sampling, I'm worried that I'm going to have all kinds of confusion about what's going on because we're not in a great place to begin with, because I think we're using too much GPU memory on the frame buffer side of things. That's my guess. And again, because of that multi-sampling that we turned on. And so just to give you some perspective on what I mean by that is if we take a look at what's going on here, remember we have four depth peels because we use depth peeling as a more advanced rendering technique to allow us to just splat sprites onto the screen in any order and still get really good anti-aliasing results around the edges, right? So we have 4 depth peel buffers. We know that those depth peel buffers are at least 1920 by 1080 when we're rendering at full resolution, and they need at least 4 bytes per pixel. But if we're honest about it, we probably want, if we're doing accumulation into those buffers, we may want more like 8, right? For intermediate results, like half-width float, or just 16 bits per gun, or something. So it's a little worse than that, potentially, right? And then we have multi-sampling turned on. So if we have like really high-quality anti-aliasing or something, and you look, if we did 16 samples per pixel for multi-sampling, it's just nuts, right? The amount of memory that it's going to take. Now, we don't have to pay for those 16 samples in terms of computing because a lot of times there's only one thing covering the pixel. So we're not necessarily going to be pixel shader bound on having to do this many pixel samples, but we are storing them. There's space reserved for them either way. And so what you can see is we can very easily get up to an extraordinarily large sort of reserved size. That's a gigabyte of GPU memory, right? And that's just too much. You know, that's not gonna work. And again, the reason it's not gonna work is not just because we don't want to require a GPU with 4 gigabytes of memory or something. Not that that isn't very common today, but it's clear that our game really shouldn't need that. But the other reason is not so much that. It's that even if we did decide that, like, hey, the heck with it, you got to have a beefy machine to run Handmade Hero, my friend. Even if we decided to do that, the bandwidth cost of working on that much memory is significant, right? So we're slowing down our max frame rate by having so much memory have to move through the GPU. So what I would like to do is just address that in a simple way. We don't necessarily have to go nuts, right? But I'd like to see if there's a way to address that a little bit more constructively first. Now, last time we did Insight, we did Children of Morta. We're back to Handmade Hero now, so I want to load up the Handmade Hero frame here. That's in our debug directory, I think. Or not. It's in NVIDIA directory. All right, I'm going to cut that and put that in our debug directory. I don't know why we need 2 directories. Let's do this. There we go. Okay, seems fine. I'll save it out. That looks right. And so I'm just going to launch the frame profiler here and see if, okay. I don't know what happened there. That didn't look good. So I don't know if that's supposed to happen on this version. Let's see if we can launch the frame debugger. So I guess we can't run it anymore. So I wonder if there's something something bad happening here. Last time we had a problem like this, NVIDIA actually fixed it for us. Maybe we can get them to fix it again. But I'm not sure what's broken there. Did I need to... Is there something busted about our project file? Maybe I need to close the project file and make a new one. I don't know. Let's try it. New project. I'm going to say... I'm going to use the complete path here rather than the substid drive because NVIDIA's substid drive, maybe the substid drives don't work. I don't know. It's hard to say. So I'm going to go in and sometimes substituted drives don't show up properly just because when you substid drive, it's per user. So if the program switches into root or kernel mode or somewhere, it won't see those substid drives. So if we use the W drive here, you can create problems with some utilities that need to run with administrator access and stuff like that. So I'm just going to double check. I'm going to go ahead and make the entire path work that way, just temporarily. It's not my preference, but I just want to give it the maximum chance of working. And so that's the only thing I can think of that I can do to make sure that that's not an issue. So I'm just doing the path to our stuff like we would normally do W handmade. So we're just doing C work handmade because that's where the substance drive is. Just making sure that that all makes sense, right? So that would be these two. And I'm going to go ahead and save that like so, and just give it one more shot. Not hopeful, but nah. So I have no idea what we're doing that's causing this problem. So I guess I won't do that today. That's what I was going to do, but apparently Insight has other ideas. I don't know what we would be doing that's so crazy. A lot of people have said we should retry using RenderDoc. Maybe today is the day we do that, because I would really like to be able to take a look at the GPU rendering here, and obviously we can do it from the other side without that, but I don't really want to. Yeah. So, I don't know. I'm going to delete these because they don't work. So, I don't know, NVIDIA. You tell me what's going on there. I have no idea. If you need something else from me, please let me know. I would like to get that working if possible. Let's take a look at RenderDoc and see if it works any better. Last time we tried this, it didn't work at all for us. It was the opposite. We were able to get Insight to work. RenderDoc didn't work. So we'll just take a look and see if it's something we can do this time, and maybe it will succeed. Again, RenderDoc is the same as Insight, basically. It's the same basic idea. It's just like an open source version that, in theory, works on other platforms. So on NVIDIA, on Insight, you can only use it on an NVIDIA part, as far as I know. Like, I don't think it works on anything else. So let's try RenderDoc and see if we get anything better. But again, the principles are exactly the same, so it's not particularly difficult to adapt from one to the other. So I'm going to go ahead and put it over here. It's installing. Okay. Here it is. I'm not sure what it wants its... let's take a look at the shortcut here. I'm not sure what it wants its actual program to be. Target RenderDoc. So is this actually not running directly? Interesting. All right. So let's take a look. If I run RenderDoc, I'm running it from the start menu here. Here's what it gathers. I'm fine with this on the Handmade Hero machine. If it wants to gather statistics, that's fine with me. RenderDoc v14. I don't have any idea how to use the interface, but it looks pretty straightforward and similar to any debugging utility you would see. The basic executable, working path, command line argument stuff. It doesn't look like, I'm just looking at it here, it doesn't look like there's like a real file menu here for saving and loading projects. It looks like maybe this is more where that happens. Just guessing based on the UI layout. So I'm going to go ahead and try here. First, we'll try actually using our paths, and if those don't work, we'll try it another way. So if I go in here and look at the build directory and have it build Win32 or run Win32 Handmade there, and then in here we do Handmade data. That is all we really need. These don't really matter. As far as I can tell, there's nothing there. We don't need child processes. We don't launch any or anything like that. I don't see anything weird going on there. So I'm going to go ahead and do save settings. I'm going to do the same thing that I just said I was going to do, which is put it in the debug directory like for NVIDIA. And I'm going to save the settings here as handmade render doc and hope for the best. So in launch applications, I'm just going to hit launch now, and we'll see what happens. So basically everybody crashes, but I don't actually know why. So I guess, like, normally I'd say, well, if we crash on both, are we the ones crashing? But as far as I can tell, what they're saying is they crashed, not us. Because presumably they know the difference. I mean, it would be fairly obvious if you launch a child process, whether it crashed or you crashed. So we're doing something, I guess, that's creating this issue. I don't know what the issue is. So there you have it, folks. That's kind of what modern programming is like. Nothing ever works, even though we're not doing anything. I mean, it's Handmade Hero. It's a... Oops. It's 32,000 lines of code. Right? But, you try to just run a thing that just inspects the GPU usage, and that's impossible. Literally impossible for a simple 32,000 line program. This is not the Unreal Engine. This is not Red Dead Redemption 2. This is just a little tiny baby little program, and that apparently is totally out of the question. And that's just how things go these days. So that's pretty sad. I guess we just can't do that. So let's go back to Handmade Hero, and I guess we'll just proceed blind. Because, you know what? That's how we used to do things anyway. You didn't used to have debugging tools for GPUs at all when they were first introduced. Kind of like when CPUs were first introduced, you didn't have debuggers probably. At least not reliable ones. So, I guess that's where we're at. So, alright, I can do this audit by hand, and I guess we just will. So let's go into our graphics subsystem here. Here's the OpenGL layer. And I guess what I would say is, let's try and add something that just sums up how much memory we're actually using, right? Because it's not that hard to imagine us keeping track of a ballpark statistic, at least for frame buffers and textures, or even just frame buffers, right? It wouldn't be that hard to actually determine what that is, because if we look through the code here, and we look for frame buffers, and we just see, like, what are we actually doing with these frame buffers, the glgen frame buffer call is going to occur anywhere that we're creating one of these, right? So if I just search for glgen frame buffers, like so, and I look at what's available there, you can kind of see it's pretty obvious, right, that anywhere we call this, we're going to be creating a new one of these frame buffers, and then when we call GL frame buffer texture 2D, we would be specifying a texture on it. But the glgen frame buffers will tell us at least which handles are available, and if we just track how big those frame buffers are, then we know how much we're spending on frame buffer memory, right? So let's take a look at all the places we actually do that. You can see here we've got one in create frame buffer, one in, this is some old, lighting nonsense, I think. So I don't know what this is doing. While text width greater than 1, text height. Why are we still doing this? Light buffers? We don't even use those anymore, do we? So we don't care about any of this stuff, I don't think. Yeah, this stuff is just old. So if we take a look at these light buffers, I think this is from our very first experiment with lighting. I don't think we're actually doing the up-down part of that at all, right? Let me just take a look at where those are actually getting used. So if we look at where they're stored, light buffers 12, I'm just curious what happens if I nuke this entirely. So I've eliminated it from the actual code there. I'm just looking to see who actually uses it. Yeah, so nobody uses it, right? So if we were to literally nuke these right here, we would be fine, right? We don't actually use them. We actually use these other, this other information here. So I'm going to go ahead and just if zero this out. Oops. So we won't actually need any of this. That will not really, I don't think, have too much of a material effect on our on our usage at all anyway. But I just want to make sure that we are eliminating things that we don't need, just to make sure we're, counting what we should be counting. Okay, so if we run Handmade Hero this way now, there should be no change because all we did is remove a vestigial remain, and so this should be exactly the same, and is. So now if I redo that search for glgen frame buffers, again we have one there and then one in create frame buffer. So really the only one then that we have is in create frame buffers, a create frame buffer, right? Because these two are now nerfed. So this is the only one we have, which means that gl create frame buffer, if we had sort of a paired version that was like gl delete, or sorry, just create frame buffer. If we had another one that was like delete frame buffer, and we just ballparked the memory that it was probably going to use, we could keep track of that memory accurately. So if I take a look at where we're doing like delete frame buffers, right? Again, it looks like it actually is paired pretty much exactly, right? Because there's free frame buffer. So that makes me think it would be pretty easy if we did something like this, where we passed in the OpenGL handle to free frame buffer here. We could just add and subtract how much memory we were actually using. So if I go to my create frame buffer call, and we sort of try to compute how much memory we're actually using on this frame buffer, we could then just store that information. You know what I mean? So basically what I want here is we would say, all right, OpenGL, total frame buffer memory or something like that, so it's tracked. The OpenGL total frame buffer memory would just add and subtract here. So we would subtract away however much memory this frame buffer maybe like this. So we would basically add and subtract away the amount that the frame buffer took, and then we would have a single variable that we could inspect that would tell us at any given time how much memory we thought we were using. It's not as good as actually asking the GPU, but at least it's like this is the amount the GPU would have to have, right? So in here, what I would do is at create frame buffer time, I would do the symmetric call, which is I'll just add in here frame buffer GPU memory used. And then all I need to do is actually come up with that estimate somehow. So when we actually create one of these results here, I just need I need to make something here which just says, what's this value going to be? So all of these have a consequence, right? So once we know each of these, then at that point we would know what the approximate memory usage is. So first of all, we know if it has a depth buffer, we have to add, well, I mean, we could just step through the process exactly, actually. And in fact, one way to do this would be to say, it initializes at 0. Let's just add in every time we attach something to the frame buffer, we add something in. So you can see when we do frame buffer text image here, and we have the format, we also have the filter type there. Filter type, I think, is... So I don't know where multi-sampling actually comes in here. Is the only thing. I guess it's the slot. Yeah, it's the slot. It's this. So the only thing that's a little bit squinky here is that we don't actually know what the multi-sample requirement is here in terms of the amount of memory. So if I look at frame buffer text image, the thing that's a little confusing is you can see here if we're doing multi-sampling, we're using this max multi-sample count, and I don't know what that actually is going to be. But it's okay because I could read it in both places, so I could basically say, like, look, let's just take that max multi-sample count and use it. Now, the reason that's a little weird, I wonder if maybe what we should do is instead of passing the slot down here, we should pass the sample count. So if that sample count is like 1 or 0, like is 1, then it's a regular buffer and it just goes through this path. And if it's higher than 1, it goes through the multi-sample path. That might be more interesting because then that way you know exactly how many samples you're asking for on the caller's end. You know what I mean? So that seems like maybe a little bit better than what we were doing. I might do that in 2 phases, but I think that's a little bit better perhaps. But for the meantime, in the meantime, what I'm going to do is just actually compute the number as it is. So the OpenGL max multi-sample count is how many samples per pixel. We would have a idea here. If it's float, it's going to be 4 times 4. Otherwise, it's just going to be 4, right? So if it's float, it's going to be 32-bit or whatever, right, per channel. Whereas if it's not, it's going to be 8-bit per channel. So that's the like texture format part times the sample count, and then we need to know the width and the height, right? So all of that put together, that is going to be our GPU memory used, and we got to add that in here, right? Like so. Now, when we get down to the depth buffer, we have to add that as well. And the depth buffer, we don't actually know how big the depth samples are, but this OpenGL depth component type here would presumably tell us some information about it, right? So you can see here 32F is just a floating point depth buffer. And so all that would do is we just say, all right, result dot GPU memory used plus equals width times height times 4. And that's probably a safe assumption. So we could do 24-bit instead, and that would be reduced. I don't know. Maybe we do this. or bytes per sample, something like that. Now my assumption here, again, is that the depth is going to be recorded per sample, because otherwise you wouldn't be able to do proper sampling. And so I think you have to multiply this by the OpenGL multi-sample count as well, right? And you can see why this is so bad. You know what I'm saying to you? We're just using way too much frame buffer memory here. It's not good. And we're going to need to get that down. I think that's probably our biggest problem right now in terms of speed. And I also don't know like what our max frame rate is, but yeah, at the moment I don't think it's particularly good, probably, right? We tried turning VSync off and it didn't really work, so that was a little bit of an issue as well. So anyway, so this would allow us to sum up the sizes of things. That's all the total size that there is, and then at the end we would just add in how much that size was. So this is actually a result there. So if I build now, I think I'm pretty good on those computations. All I need to do is add these variables in where I said they were going to be, right? Oh, and then I need to actually make frame buffer. When we call free frame buffer, we need to pass in the OpenGL handle. So, like so, right? So that's pretty much it. Let me go ahead and add those values in here to the, the various places they belong. I'm going to add in here total GPU frame buffer memory. I'm going to make this a UMM because, again, if we're summing up GPU memory, we don't, we could, in theory, at least during testing, be using more than 2 gigabytes, more than 4 gigabytes even, if you were doing some crazy stuff. So we don't want to wrap an integer or an unsigned integer. So let's just record it as a 64-bit value. It's obviously not important to do so in the normal case, but I feel like we should be overly cautious there. So those will be tracked as 64, just in case, even though we probably don't need it in this particular instance, because I don't think we're getting up over 4 gigs. But so if we run this now, and I just compute that value, in theory it's computing, but we don't have any way to see it. And so what I'd like to do is put that in here. You can see we're dumping some random rendering stuff. We don't really dump much of value here, but you can kind of see, oh, in fact, there we go. This time we actually were able to get VSync turned off. It does look like we get some faster frames, maybe a little bit. Hard to say. So what I'd like to do is be able to print that number out, right? So I'm going to go ahead and add in something here where we're actually doing our debug values there. I'm going to try and print that out. And if I look at the debug values for that, I don't actually know where we've been putting those. Oops. At the moment, why don't I see the renderer stuff in here? Shouldn't we see the debug data block? So this is the data block. Oh, because they're all Booleans. That's why. So I think if I just open this data block inside the OpenGL renderer and put forth the information, I think that's probably all we really need. So if we take a look inside the, probably the actual frame update call, I guess would be the, don't even remember what the frame end is actually called. It's not end UI frame, OpenGL end frame. So in OpenGL end frame, here is where the actual meat of the rendering takes place. So what we could do here is just say, look at the end of that or something, let's update that variable. So, you know, I could just say, all right, at this point in time, we've got OpenGL total GPU memory, total GPU frame buffer memory. And in theory, we could sort of put that forth, right? Although I guess, now that I think about it, I don't know if we actually... There is a little bit of an issue there, which is I don't know that we actually have the debug stuff wired up in here. I don't know if it would actually work correctly because this is a separate DLL. I don't know if we actually took the time to wire it up for debug output that way. We probably didn't because we tried to make it stand alone. So what I might do is not quite that then. What I might do is just make it so that the platform renderer part of things contains it, and then someone else can print it out, right? So in here, like in this platform renderer header, I think I might just put it in there. So it's in the header instead of anything else. So there's just some vague like statistics, you know what I mean? So in here where we have platform renderer, I'm just going to put this in here. Something like this. All right, so if I go now and force it to use those, instead of like, you know, OpenGL arrow total GPU frame buffer memory, now it's going to be like OpenGL like header, right? And same within the other place where I'm actually using it, OpenGL header total frame buffer memory. Right. So at that point, I've pretty much got it in a place where now I can just output it with the rest of the stuff that we're doing. And so in here, we should be able to do that because since we have the platform available to us, we should also be able to get the renderer information from there, right? So when we look at the platform renderer, we should be, I assume we have a way of accessing that easily. I guess now that I think about it, I don't actually know that that's necessarily true. We may have to make sure that that also gets passed through. I mean, it should have, but I don't know that we ever actually did that. If I take a look for platform renderer, I'm just not sure where all of that goes in. So yeah, if you look here, the Win32 call that actually does this, Win32 in a default renderer there, you can see in Win32 Handmade we're calling it. I'm not actually sure we ever tell the application about that. Now, technically we don't have to. So I guess we just won't, because in here we can output the debug information just fine, which should be reasonable, right? So in here where we go to do like our end frame call, that's presumably the only place we would really need to do it, right? So I'm just going to say let's do it that way. So in here where we go into frame display, that seems like probably the right place to put it. So, you know, we do an end frame, and then we record these values for next time. Or maybe we do them right before the end frame. I don't know where the debug collation actually occurs. Maybe we do it before the debug collation. So maybe we do it like right here. So maybe before we collate, we just stick them in here. So let's just open that same block. So much like we were doing here, we'll open this block and output some debug values. So we know the renderer has the total frame buffer memory used, and we can also go in and add the texture memory usage as well. Ambiguous call to overloaded function. Oh, probably because these are UMMs. Which I don't know, do we not support that in our debug data? No, we do. So it look, we could easily have a size for that, but at the moment, it looks like we don't, right? So I guess, yeah. So that's a little bit annoying too. So we don't currently have a UMM sized variable here. Like we only have a U32 sized variable. I don't really know why we did that, because you'd think we'd want to store a U64 as well. But that's the reason that this is, having trouble there. I'm tempted to just add one. If I look at all the places that are using debug U32, you can see that really it's just this. So in theory, if I just wanted to do that, right? In theory, we could do something like this and just have a value U64 that gets printed out here. Now, I don't actually know when we do a format string, I don't know what we made for 64-bit printout to the extent that we did. I'll look if we've got one. But even if we didn't, we can still do sort of a cast and print, or do it as a float there, for example. In fact, I could just make these floats and be done with it. But we'll see. So let's take a look and see, did we actually do any 64-bit printout here? Did we make it easy for ourselves to do that? So it looks like X, anyway, pointers print out S64. M for memory. So you can see we actually did a memory thing here, and we actually do gigabytes. This is perfect. This is exactly what we want. So what I would do is I just say, look, let's do it actually as a debug type UMM here. Let's actually just do that. So then in the debug interface, we would have debug type UMM, which is our memory type that we print out. That would be perfect for what we're doing here, because this is a memory size specifically. So that seems good. And then in here, we would just need a place to store it. So value UMM, like that. I think that's really all we would need to do. And so in here, where we have this sort of, set of things that are, basically just garbage, because C and C++ are pretty terrible at this sort of thing. We should now have a way of recording memory-sized things into the debug stream and printing them out as memory sizes. Pretty simple, but probably worth it, right? So here you can see this is the disaster I was talking about. We don't know we don't know if that number is correct. So, I mean, I could be computing it incorrectly, but it probably is, right? Because remember that back of the envelope calculation I did, 1920 times 1080. Let's see what the max sample count is, actually. I guess I don't know what that is. Do we have that on here? We don't. So let's forward that value out as well at the moment, because, that's kind of a disaster there. So if we go in here to Handmade Renderer, I also want to put, like, maybe like something like this. So here's what it decided to use for a multi-sample count. I'll just shove that in there as well. So then inside OpenGL, when we're actually, Handmade OpenGL. Nope. Render OpenGL. When we're actually sort of doing the change settings, we can actually look to see, like, okay, what are we doing with the multi-sampling, and what is that number going to be, right? So in here, we can specify what that number is. When we use OpenGL multi-sampling here, and we put in the depth peel flags like this, you can see, I can just go ahead and set the header there to show which one we're using. So in our OpenGL, oops. header dot used multi-sample count, I can just say, hey, the multi-sample count that we're actually using is that max, right? Max multi-sample count, that thing. And if we don't use multi-sampling, then it's just going to be 1. And then when we print this out in handmade.cpp, exactly like before. Oh, sorry, no, it wasn't there. It was here. I'll print that out here. And so in theory now we can also see what that multi-sample count is. Then we can do the back of the envelope computation correctly. It would be nice to verify this value, but you know, without nsight or something, we can't really verify it. So we don't know that it's actually correct. But if it's 16, which is the highest possible multi-sampling, then what we've got here is exactly what I thought, right? We have 4 depth peels at 1920 by 1080. Each one actually has 4 times 4, because it's 4 bytes for a float times 4 RGBA, right? So that's 16, right? 4 times 1920 times 1080 times 16. And then each one of those is 16 samples, right? So in addition to those 4, we also have the depth buffer, which I guess... So the thing that I'm not sure about is the depth buffer, we wouldn't need 1 per frame buffer. The depth buffer would be the same for all of them, right? But I'm not sure at the moment if we're actually smart enough to be doing that. So I'm pretty sure even that actually goes like this. Right? So I'm pretty sure that actually this gets added in there. And so it looks like back of the envelope wise, we are like using at least 2.4 gigs, and it's just absurd, right? It's just totally unacceptable. And so we need to start reducing that number pretty dramatically, obviously. And there's a number of ways that we could do that, and we should start by, kind of addressing as much of that as we can. So if we look, I guess a couple things here. There's a number of things we could do. The first one, I think, is probably the most sensible, and it's a little bit tough to do, but I think we should at least try to get it working. And that is that we don't actually need to store multi-sampling after our first pass, right? If that makes sense. By the way, I noticed, I just happened to see out of the corner of my eye, someone's asking why there are 4 channels in the depth buffer. There aren't. This is just 4 bytes for the floating point value that's stored, right? So anyway, the depth buffer, I don't even know that we would need to keep the depth buffer. Like, in theory, we only need 2 depth buffers, right? So in theory, we only need to store 2 depth buffers, the one that we're on right now and the one that was for the previous pass. The reason I say that is because obviously when we're doing the rendering pass, we need to record our depth buffer, and we also need to look up and check against the existing depth buffer to see whether or not we're past it in order to do the depth peel properly. But once we compute the depth peel, we don't need to know that anymore, because I don't think we use the depth information when we actually do our final composite, right? Am I wrong about that? see. So here you can see us sampling it, right? So we don't, when we actually blend the four depth buffers, the four depth peels together, we don't need the depth buffer anymore. So we really only need 2 depth buffers total, right? So I'm just going to come up with a ballpark estimate here, right? So let's say we retained 2 floating point depth buffers, which we could probably get away with 16-bit just fine. But let's say we used full float or 24-bit, but full float, let's say. Anyway, so worst case scenario, full float. So we need to have 2 depth buffers times 1920 by 1080 times 16 samples times 4, right? Is what we would need. So checking out how many gigabytes that is, you can obviously see like it's drastically less, because it would have the number. It's still not great. So I do wonder a little bit again about just trying to think if there's like going down to a single one of those would be preferable, certainly. You know what I mean? Getting away with that would probably be the best possible scenario for us. Just trying to think it through. Because I think you want multi-sampling and you want a depth buffer, and you want to use the depth buffer with the multi-sampling. That all seems true. Now, you could get away, I think, with just 1 at that resolution, because I think once you're done with it, you can map it down. You could just assume that pixel had whatever the depth was on the largest pass. So I think we could get away with just 1 multi-sample depth buffer, actually. And that would be, what's that, like 128 megs? Yeah. So 128 megabytes for the depth buffer isn't awful at 16x multi-sampling, which is very good multi-sampling. So let's say we do that. We would then also need 1 resolved depth buffer, but that would be trivial. It would be like that or something. It would be like 8 megabytes. No one would care because it would be unmulti-sampled. So I feel like that would work if we went that route. I mean, we'll see, but I feel like that would work. So I think we could get it down to 128 megabytes for a depth buffer. And that would be a savings of 4x, right? Basically. But that's the small potatoes, because the color buffers are really the huge thing. And a single color buffer right now is 1920 by 1080 times 16 times 16, right? And so a single, just 1 color buffer, just 1, is half a gigabyte. Right? Just 1 color buffer. And so a couple things we can do to attack that. The first one is, obviously, we can reduce the number of multi-sampled color buffers we store. And so again, I think the answer here is going to be draw a depth peel with multi-sampling on, but then resolve the multi-sample down first. Because after we do the depth peel, we don't need to keep that multi-sampled stuff around. So just have 1 and do it and be done. That would get us down to half a gigabyte rather than 2 gigabytes. So it's a good first step, but half a gigabyte is still way too large. So the next question is, can we stop storing floating point information? Well, obviously we don't need float for the alpha channel. That's absurd. We only need an 8-bit value for the alpha channel. But for the color channel, I don't know. We could certainly switch away from float right now, and it wouldn't really do much harm. But we may in the future want to have better lighting information recorded. And so I think keeping at least 16 bits per sample would probably be important. It's hard to say. Whether we could get away with a 10 bits per gun kind of a sample format or something, or 11 bits per gun or something like that. Because there are some hybrid formats that have that sort of thing. Maybe. But if we went down to 16 bits per gun instead, that drops us down to 256 megs, which isn't bad. Again, all of these numbers become trivially better if you just reduce the multi-sampling count. So this is only the highest end system that would be running a 16x multi-sample, right? On lower end systems, we can drop the multi-sample down or turn it off entirely, and the graphics just look a little crispier. But then then your memory usage drops by 16x, right? And it's all nonsense, right? If we just got rid of the multi-sampling, you're down to 15 megabytes, right? So it's the multi-sampling that's really killing us, but we're trying to use it to give a really high quality image, and so we do want to have that be available. Now, there's another option we could think about here, and that is that multi-sampling is only necessary for objects which themselves actually don't need to be depth field, right? Multi-sampling is unnecessary for our sprites. Our sprites we can critically sample properly just by using bitmapping, and they do not have geometric edges. So the only thing we're using the multi-sampling for right now is our cubes. So the question is, if we wanted to say that our cubes cannot have alpha, right? Cubes are solid. If we just say that cubes are solid, then we can actually do something even better than any of this, which is we can draw cubes only in like solids only, basically, with multi-sampling, and then alpha things we turn the multi-sampling on and the depth peeling on. I'm sorry, we turn the multi-sampling off and the depth peeling on. So we would not use multi-sample frame buffers for that process. That would lead to a pretty nice way of running things, which is to say we have a single multi-sampling buffer. We render the cubes into it with depth peeling turned off. We resolve it, and then we just use that as something we composite our alpha things with at the end. I like the sound of that, right? I like the sound of that, and I think that might be a good answer. Because actually, if you did that, you could still use cubes with alpha on them if you wanted to, and they would just go into the other pass. So you wouldn't get multi-sampling on cubes with alpha, but that's the only restriction. Everything else would just work, right? That to me sounds pretty compelling. I think that's what we should do. That's my argument. That's what we're gonna do. So here's the way we would do this. So let's suppose we took a look at this information right here. So I think effectively this compositor would work exactly the same as it does now. If we went down to the multipass part of the rendering, so here's where that happens. When we first set it up, so you can see here we do like the full clear and we begin the peels. What you can see here is we say, look, when we are doing our depth peel, and I don't actually know. Yeah, here's on peel index. So when we are doing our depth peel and we're working our way backwards, what you can see here is that the load. So if we're peeling, right, the load of the depth handle doesn't occur if we are on the first depth peel, right? So it basically says, you know, when we go in here and render, we're gonna make sure that we start loading from that depth peel, and off we go. Which I guess we still sort of have to have happen. I'm just trying to figure out how we would actually load in these, how we would get these cubes into the system, though. So I guess what we do is we just render the image as its own depth peel as part of the depth peel process. So I guess what we do is when you get to the end, so yeah, okay, this is what we do. So when we get to the end of our depth peels, we then render one full screen quad that is the texture of our pre-render of the cubes, right? So we render the cubes. We have now a frame buffer and a depth buffer resolved that are just simple 1920 by 1080 by 4, so very small. We render those in the pre-pass. We then just composite those in when we're doing our depth peeling every time. So we just do one full screen quad to basically like blit that in into the depth peel so that it gets properly sorted into that depth peel. I think that's the best way to do it. I think that's probably the best way to do it. I can't think of anything better than that. And it's pretty cheap, right? One full screen blit on modern graphics cards is actually fairly cheap. And it's just going to run a simple fragment check. So basically, like, you know, this fragment code here, it's just going to do this. Right. It's just going to do that compare. So does that work? I think it does. It seems awfully complicated, though. I'm just trying to think if there's some simpler way to do this. But I can't really think of anything simpler. I mean, I think we basically have to split off the rendering into things that require multi-sample and things that don't. So here's a question. I mean, is it smarter to just store the depth peel's depth values, and then when we composite, just insert the cubes in where they belong during the final composite? And I don't really know. But you can see what I'm getting at there, hopefully. When we render these, we're effectively going to have, 5 images, if you will, if we just talk about the abstract content. One image is the 3D geometry, which, when rendered through multi-sampling without any depth peels, is just correct, right? Or the solid geometry, I should say. So stuff that doesn't have alpha in it. It's correct because the multi-sampling took care of the blending along the edges, and so it's just correct. It's as good as it's going to get. So if we have that image, we then have our sprites and things with that have partial alpha, so edges that are defined in the bitmap, or translucency, or transparency, right? Where you can kind of see through them or see through them partially. When we do those we are constructing 4 peeled images of, so that we can blend them together at the end. And I guess even as I'm saying that, I'm realizing, why do we even need to do that? So probably we just did this for expedience, but if you think about it, we actually don't need to do it that way at all, do we? A depth peel can do its blend when it's done, right? Because look at the compositor. The 0th peel, which is the frontmost peel, right? If once you know what that peel is, you know exactly how much alpha you have left for the next peel. So, if I'm not mistaken, we really only need 2 depth peel buffers total, no matter how many passes you do, right? Because all you would need to do is just render the first one. When you render the second one, right after you're done rendering it, blend it back into the first one using however much alpha is left. You then update the alpha channel with the remaining alpha left, right? And repeat the process. I think that's all there is to it. At least I'm pretty sure. Right? So I think, actually, now that we've kind of worked this out, maybe what we should do, we're kind of running out of time here. Maybe what we should do tomorrow is say, let's convert our depth peel renderer into using only 2 depth peels. And at that point, we would reduce our memory footprint immediately by half, which would be a good start. And I guess I'm not sure, it still seems at that point it's not going to be quite small enough. So, again, looking at, just trying to do the back of the envelope here to get roughly what we should have. So if we were to take our original equation here, which looks like this, so I'm copying it back in. So if we take a look at this original equation, And we assume that there are 4 sets of these, and that's what was giving us this. If we drop down to 2, it's 1.2 gigabytes, which is still too high, in my opinion, right? So looking at where the fat comes in, you know, this number, like I said, could be dropped down to 8 pretty trivially, I think, without a lot of work. That gets us under a gigabyte, still a little bit high. And so the question is, can we reduce it further? And again, I think the answer there is we can drop it down to a sum of 2 of these by just changing the way that we do the depth peel. So instead of the depth peel being multi-sampled, I think we can condense the depth peel into being recording the multi-samples only for the pass it's actually on. And I think that's probably fine. It may be a little loss of quality, but I think that's probably fine. I want to do a quick check as the last thing we do today. So for a create frame buffer, I'm curious how many of these we actually have. So if you take a look at what we've got here, you can see that we have, for each depth peel, we're creating either, oh, what's this depth peel resolve buffer as well? So wait a minute, are we already doing a depth peel resolve? Wait. It's been a while since we looked at this render. So actually we're doing the resolve already. So wait a minute, so did we just not bother to throw away the set of frame buffers we were using? Hold on. If we resolve at the end of every single one of these, then we don't need a different one for each depth peel, right? So if that's the case, then like in here, right, where we do the clearing each time and we bind this buffer, I guess I'm just not sure. Can we just do this? I'm just going to look at resolve multi-sample. So in here we say bind the from's depth handle and the color handle, and then we're going to begin the screen on the 2 frame buffer handle. But is that... I guess what I don't quite understand though is, yeah, that's the resolve buffer. So I'm just curious, if we just do this, so we're only ever using the first one, does that work? So hilariously, we already had implemented exactly what I just said we should start with. And as far as I can tell, let me zoom in on some overlapping stuff here. That looks pretty darn good. So I think we can reduce our usage basically for free right now because we already did the work and just never bothered to throw away these buffers, probably because we saved them just so we could view them for debugging or something. But basically that means the depth peel buffer here can just allocate only one, right? So we would just do this. I want to say. Again, just going through and quickly making this slight change. So I'm not sure if anyone uses get depth peel read buffer. Looks like we do here. So in get depth peel read buffer, it looks like there's a slight issue with this, which is that if multi-sampling's turned off, maybe this doesn't quite work, and we might have to like do a little bit of massaging to make that happen. So I guess I don't really know, but I think we want to do this. What would that... Why does that have to be an address of? That's a bit weird, but all right. Okay, so let's just try running this. So if I take a look at what's going on now, I mean, I don't know, that image looks pretty high quality to me. I don't see really much in the way of degradation there. And everything seems to still be running correctly. Right. So if we take a look at our render usage here, in theory we dropped, because I think it was 3 point something before, and now it's 2, right? So in theory that got us down already just doing that. If we turn off request vsync, I'm just curious what our frame rate is. It probably didn't change much, but... Yeah, it didn't really look like it affected that much, but... So that's pretty weird and wild, but it looks like we kind of got some of that for free. Now, in terms of where this 2 gigabytes coming from, I'd like to kind of know roughly what that value actually is, and so I'm going to step through the code real quick, as the last thing we'll do today, just to understand what's going on there. So I'm going to take a breakpoint in create frame buffer. I don't know if it's create frame buffer cap. I think it might be actually create frame buffer lowercase. All right. So I want to take a look at this code here, and what I want to do is just see how much memory it thinks it's using. So if we take a look at the result here, it should start off at 0, and it does. We add in one of the color buffers, right? And so we would expect that, let me just double check what the width and height are, yeah. So we would expect that to be 1920 by 1080, and we would expect it to, currently it's float, right, I'm assuming. Oh, this is not float. So this is our resolve buffer, which is the actual screen one. So never mind that. Let's just step out of here. So the OpenGL resolve buffer should be a negligible size. And let's just make sure it is. So 1920 by 1080 by 4. Why is that? That seems too large for the resolve frame buffer. So I guess I do want to step in there. Sorry. What's going on there? Why can't I set this breakpoint? Oh, there we go. What? Did I do something? I'm getting all confused here. Oh, you know what I just realized? I wonder if that's what was happening. I wonder if because we set that directory incorrectly, because we changed it from handmade data, didn't we? You know what? I wonder if I've been Herman the whole time, or Herbert the whole time here. I don't actually know. They still shouldn't have crashed, but that's probably what happened. So in here, I think when we set this up originally, the problem was we changed our working directory. So our working directory is this now. Oh man, so we could totally have profiled this. Ah, that's an owl's shame. So basically, like, I don't know why they didn't say we crashed, but I guess it was probably just that we were, I don't know, sending something down bogus when we don't have our working directory set up properly. We probably, like, called something that they didn't like, and so we crashed them before we got to a point where our app would crash or something, right? But yeah. Okay. So let's see if we can actually verify our numbers at all here. I don't really need the performance counters at the moment, but thank you. Oops. Okay. So actually, we're fine. So let's go now and see if we can get it to tell us how much memory we're using on the GPU so that we can corroborate that number a little bit. And we're not counting the texture memory yet, so we should probably add that in there. But anyway, let me go ahead and do what I was doing a step through, and then we're going to run through Nsight at least once and get that information. So if we take a look in here, like I said, I wasn't sure why this was so large. So, I see what the problem is. We're using OpenGL max multi-sample count even if multi-sampling is not enabled, right? And that's wrong. So that's the problem right there. So we're overcounting for buffers that actually aren't being used for multi-sampling. So what we want here is multi-sampled. We should actually take the sample count here. Like so. And that way we can say, okay, let's just multiply by the sample count. And we now know that that is set properly depending on which one they ask for, and we won't overcount like the frame buffer, the regular actual like thing we display on the screen, that won't get counted as wanting multi-sampling, right? Okay, so now we should see, hopefully, we should see this frame buffer as a much more normal size. mode here, or we can't inspect any values. And step out. There we go. So now I think we're computing these values more correctly. Let's take a look at one of the ones that does have stuff turned on. So here's a sample count of 16 probably. Right? And so in here, when we sum these up, what we would expect to see is 1920 by 1080 times 4. I'm sorry, times 16 times 16 for the color buffer, plus 1920 by 1080 times 4 times 16 for the float, for the depth buffer, something like this, right? And let's see if that's at all what we actually saw. Did I do that wrong? 1920 times 1080 times 16 times 16 plus 1920 times 1080 times 4 times 16. I think that's correct. Let me do it in speed crunch first. So I'm not sure how it got this value. Or how I'm getting the wrong value. So I guess I'll double check my assumptions. Is float. So this is not float. So that's the reason. This is a non-float multi-sampled frame buffer. Who is asking for this? I'm sorry, I want to depth peel flags. So who is asking for this? And I thought we were asking for float. Did we turn off float usage or something like this? A depth peel flags of 5 in the renderer. I would agree that does not appear to have floating point turned on. So actually, that computation is correct. So we're not using float? Then how are we adding up to such a large number if we're not using float? It should be smaller. Where are the depth peel flags? Yeah, so it's not actually using a floating point frame buffer. Interesting. So how are we getting such a large number then? Let's keep going at this. So I'm going to return the result here. If I look at OpenGL depth peel buffer, that's less than I was thinking. We're going to make 4 more of those. So we should, yeah, it doesn't seem like we should be getting to 2 gigabytes this way. It should be like 1 gigabyte, right? Because it's not using float for anything there except maybe the depth peel, I guess the depth peel buffer. All right, so that's a bit odd. Let's take a look at OpenGL total, header. And take a look here, right? So there's the total memory, and it's going to go up now. 1, 2, 3, 4. And that's it. So that number just is not commensurate with what we were seeing, I don't think. Is there some other? No, I don't see it. So if we say 340,070,400 divided by 1024 times 1024 times 1024, am I miscounting the zeros there? Am I going crazy? That to me looks like 340 million. How is that getting 3? Oh, pfft. Wow, what a typo. So that is actually quite low. Do we have the same typo in our printf somehow? How is it printing out such a high number? Or is it not printing out such a high number anymore? But I thought it was printing out like 2 megabytes or something, or 2 gigabytes, right? No. Okay, so I guess we just didn't recheck it after doing that or something. Okay, so now we've drastically reduced it. I didn't realize we weren't using float. So we're much better now. We've like drastically reduced the amount of frame buffer memory we're using because again, now we don't actually store those huge multi-sample buffers for every depth peel for no reason. So we've gotten rid of that multiply by 4 that was happening there. So that's actually a good start. And we were over counting before, so we weren't as bad as we thought because we were multiplying by 16 every time instead of only the times when it actually was turned on. So that was drastically inflating our number. But so now at least on this GPU, we can still do better than that, but now on this GPU, I'm not worried about that anymore. We can keep going at that level, and that's totally fine. So this is actually a surprise mission accomplished in a sense. And now what I'd like to do is just take a look at what OpenGL actually thinks is going on if we can. So I'm gonna now take just a quick look at that end site that I wasn't able to do before because we had set the value wrong. Just the working directory wrong. We should just put in something that pops up a message if the working directory is wrong, because I don't know what actually happens when you do that. In fact, let's find out. We should just find out at some point. All right, so let's run this through Nsight, see what it has to say. Also, I think we can turn on the profiling options as well. So like if we go in here and we try to do the launch frame profiler, I think it will tell us that it can't access the GPU counters or whatever. So we'll see. But if we turn vsync off as well, so let me go in here and see about asking for vsync off. Right. So here's the information about how many milliseconds per frame it thinks we're using. And there's me hopping along. And so not a horrible render time, but not great. I mean, we can improve it, certainly. But, let's go ahead and see if we can't get a capture for live analysis on here. Okay, so here's the problem. So this is the thing I was talking about where we don't have permission to access the GPU performance counters. So if I remember correctly, this is actually pretty trivial to enable, though. You have to install like special drivers or anything. So if you want to be able to access the performance profilers, I believe you just go into your settings. Here we go. I believe you just go into your settings and turn on the developer settings on the driver, and they allow you to enable these. So I think for those of you watching at home, I think we can just do something like this and get access to those. It's not like with vTune or something where sometimes there's some hoops to jump through. But so on here, you can just go to enable developer settings like that. And then you get additional features in here. You open this up and you can say allow access like so. Hopefully you can still see the stream. Let me double check to make sure that didn't bogart anybody. Yeah, looks okay. right? So now you have access to the performance. The GPU performance counters can be accessed by our tools that we run. And so now I think maybe, possibly, if I relaunch, I don't know why it thinks it crashed there. There we go. Let me try running it again, and we'll see if it can actually avoid that error message. So let me launch the profiler. And I think now we're okay. Get rid of this. I don't know where nSight went. It seems to have disappeared, which is not reassuring. Yeah. So that didn't go so well, if we're honest about it. Try that one more time. Okay, so it worked that time. Maybe we just had to restart after changing the driver settings. All right, so once we're done getting this all configured, I assume we can do a capture for live analysis and take a look. There we go. Here is the readout of all of the OpenGL stuff we've got, right? And if we take a look at the profiler view here, we can see that it tries to give us some information about who took what time and where, right? I'm actually more interested, just as a quick look into what's going on, if there is a way to get a total amount of GPU memory committed as a part of this, right? Just because, like I was saying, it would be nice to validate our numbers. Those are just numbers we made up by counting ourselves. But it would be best if it could tell us, hey, here's how much memory we think you're using. I don't know what this is here. Is there a red flag? Oh, it's just that. But I don't see much like this is, I believe, just telling us how much throughput there was. I don't think that's telling us how much total we've added that we had in there. So I'm not sure. You have to forgive me for not knowing my way around nSight as well as I probably should. I'm not seeing a whole lot of information about that. Here's the API statistics, but it doesn't really, it just says how much time was spent, and it doesn't say how much memory they ended up allocating out. Here we've got, again, a good layout of the time taken to do things. Again, not really what I was looking for. And presumably this is just based on, oops. Which one of these I select, right? I seem to have got it thoroughly confused there. Okay. So if I select one of those, right, it's going to show me the statistics for this particular call. And it's not really what I wanted to know. So I don't see, sadly, I don't see a good way to get totals. You can see here, right, there is a memory value that's on there, but it doesn't tell me a combined memory value that just says everything. And it's probably not the most fun thing in the world to scroll through these and ask for each one. You can see the depth peels are now only taking 8 megabytes. That was really nice. I would say oh no, that's what we expect, I guess. Yeah. So looking at the frame buffers themselves, I guess, oh, those are not frame buffers. Those are buffers. Let's go to drawables. Unsurprising there. Yeah, so I don't know. Here's that's a bunch of unrelated stuff. So I can't even find, I guess, oh, there we go. So these are our actual front, like our actual drawing buffers. There's the depth buffer. With the multi-sampling, right? Yeah, so I don't actually know any way to get this to sum them for me. But it looks like it would add up to roughly the same amount because, right, you've got two buffers here, each of which are 128 megabytes. That's 256 megabytes. And then you've got like some stragglers here that presumably, as you add it up enough of those, you get up more towards the 300 megabyte range when you count the final resolve buffer and all that stuff. So I guess seems like it correlates at least close. Probably not too far off anyway. I would say I'm seeing one less than I expect to see because I expect to see the final resolve buffer in here. I don't see it, which is weird. You know what I'm saying? So I don't know. This isn't perfect view. I would like something better. If we look at the actual just regular profile view in here, you can see it. I don't quite know why there's like a bit I can't see off the end. That seems less than good. I don't know if that's just because it's docked weirdly or something. No, it seems like it's just drawing it as a tiny little thing, and you have to zoom in order to scroll it. So that's by design. Put that back over here. So actually, that's not where that went. It went right there. So looking at this, you can see the time is spread sort of exactly as we would expect, I guess. I think like that's the first depth peel, second depth peel, third depth peel, fourth depth peel, right? And so each depth peel takes 1 millisecond to draw, so 4 milliseconds total. And then we've got some extra stuff in here for like prepping and clearing and stuff like that. Let's see what this is. I don't know why. So that must be submitting that. So it kind of looks like if that really is taking all that time, it looks like we could actually save a non-trivial, like not huge, but non-trivial amount of time by submitting the vertex buffer more cleanly, because it looks like it thinks it has to retransform it every time. Also, I'm just looking at that, and that's probably an OpenGL thing, right? Because we didn't lock it down and say, hey, look, we're not touching this. So I think it has to retransmit it every time. So that we could save, a millisecond or something off of our time, which would not be insignificant. But if you look at it, like the actual drawing time, I feel like these here, just looking at that, at those vertex element base calls, I don't see any reason why you would be paying that large of a price for those. So I feel like we could go in and get rid of a little of that fat too. In here, if I look at, in fact, maybe it'll tell me too if I look at where it's actually spending the time there. So maybe, I don't know, maybe that's not what that's telling me. I'm not sure. But, if I just look, at it, it feels like we could save time there by just telling it, look, this is the same thing. You can pre-transform it once into temporary memory and not have to ever run any of those shaders again. I don't know. That might not really matter. Again, I'm not familiar with using this profiler, really, so I may be just misinterpreting what it's actually saying. But anyway, you can kind of see that there is some cruft to clean up in there, even beyond the call. If you look at the actual call itself, it looks like, at least in here, you can sort of see like the vertex attribute fetching and the primitive dispatch and stuff is totally like not implicated, right? So in here you can see this is presumably like a shading unit here. This is how much texture fetch time is going on here, right? You can see there's a fair bit of that. I don't know if we can inspect specifically and say how much time is in like a pixel shader specifically. This is the shading engine, I assume, just telling us what's going on in there, right? So here is this is like a clear, or a resolve rather, right? Wait, is that true? So vertex shader invocation is 4. Wait a minute. So I'm interpreting this backwards then, depending on how this looks. So these drawing calls are actually just the ones that have all the time listed are the resolves. There's no way it's taking 1.27 milliseconds to do a resolve, is there? Well, I guess it has to pull through 128 megabytes of samples, though. Yikes! So you mean to tell me that if this profile is accurate, this, which is drawing all of the data, right? There's the 65,000 vertex shader invocations, right? And just looking at that, am I to understand that that was basically free, and that no one cares, and then like this this triangle strip to resolve the multi-sampling, that was the thing that took the time? I guess what I would say is, I don't know if I believe that. It seems not very possible. I mean, I could construct an argument for why that was true, but it would be a bit of a stretch. So I'm kind of thinking that doesn't make a whole lot of sense. So I don't know about that. I don't know if I believe that's actually true. So I would probably take that with a grain of salt, but who knows? If that were the case, then that basically just means that we need to speed up the multi-sample resolve. That one is what, the clear? I don't know. I'm not super convinced here. I don't know if I really believe those timings. I would have to get a GPU expert to tell me if that was really plausible, because I don't really know if I believe it. It doesn't seem likely, just based on what that was showing there. So maybe that's not super useful. But hey, at least we got it rerunning, so that's nice. All right, so I think we've done what I wanted to do, which was get that memory usage down to a sane level, which turned out to be free after we analyzed it. It looks like we had already done the work. We just never actually removed the old buffers, probably for debugging reasons. We left them around so we could see them more easily or something. I don't know why we did it, but we probably just weren't thinking about memory usage at the time. And so actually we'd already done the work we needed, and it was pretty simple for us to just go ahead and turn off the intermediate storage. So now we're much more sane, and we're hitting the graphics card a lot less hard, even just already. So that's great. So tomorrow what I'll do is I'll put in some pixel shading there that tries to simulate the sampling of those light probes, even though we don't really have the data for them. We'll try and like sort of pseudo simulate what's happening with those. And then we can go and see how much that's going to cost us and just get a ballpark on that. So we'll do that tomorrow. Until then, I guess what I'd say is sorry to have that be a little anticlimactic. I thought we would have to actually do some work there, but it turns out we were smarter than we thought we were, and we had already laid the groundwork for it. So that's a good sign. Anyway, we'll come back tomorrow to do that, to just start the work on the pixel shader and see how that performs or changes the performance profile. It would be nice to see why we're taking so long per frame, and that profile that was shown there didn't really illuminate why that would be. My suspicion would just be because, again, it's a lot of memory to chew through because we're doing that really heavy oversampling. But that's something we can pretty easily check. And so if we just go in and turn the multi-sampling down or off, in fact, we might even be able to do that pretty easily. I don't know if our multi-sampling button actually works yet because we've kind of mucked around with it. But if we take a look at the frame time, we turn VSync off so it's rendering as fast as it can, right? If I go in there and turn multi-sampling off, well, that's not, all right, never mind. So we do need to go fix that multi-sampling read. That was the thing that I put in the to-do. So what we should probably do tomorrow is fix that multi-sampling read, look at the difference in time between multi-sampling on and off, and just verify that the frame rate increases as we back off of multi-sampling. If it doesn't, then the extra bandwidth, extra sampling time, but mostly extra bandwidth, because most of the time multi-sample for us probably isn't actually taking additional samples. So the extra bandwidth there, we'll be able to see that was actually the case. And so rather than just assuming it's the case, I'd like to go in and actually try and verify that. Backing off the multi-sampling clearly produces the improvement in rendering time that we would expect. And if it doesn't, then we're going to go on a little bit of a hunt to find out what's actually the problem, right? So we'll do that tomorrow. Hope to see you back here for that. Until then, if you want to follow the series at home, you can always pre-order the game at handmadehero.org. It comes with the source code already, so you can play around with it as we work on it. Yeah, until tomorrow, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.